Welcome back to SCI Discovery Chronicles, where we unravel the mysteries of the universe one scientific enigma at a time. Today, we are diving into one of the most perplexing puzzles in modern physics, the black hole information paradox. Black holes have fascinated scientists and the public alike for decades. These cosmic giants, with their overwhelming gravitational pull, devour everything that comes too close. Even light itself can't escape. But lurking behind their menacing exterior is an even greater mystery that has baffled physicists for years. The question at the heart of this paradox is simple: can information really be lost in a black hole? Or, in other words, what happens to the matter and information that a black hole swallows? Does it disappear forever, or is there a way to retrieve it? In this video, we're going to explore the fundamental concepts behind black holes, why this paradox matters, and what some of the greatest minds in physics, like Stephen Hawking, have to say about it. By the end, you'll have a deeper understanding of why this issue is so important, not just for understanding black holes, but for the entire fabric of the universe. Let's begin. Section 1. What is a black hole? Before we dive into the paradox, it's important to first understand what exactly a black hole is. A black hole forms when a massive star exhausts its nuclear fuel and collapses under its own gravity. The result is an object so dense and with such intense gravitational pull that not even light can escape its grasp. This is why we call them black holes. They literally appear black because they emit no light. But black holes aren't just empty voids in space. At the heart of every black hole lies a singularity, a point of infinite density where the laws of physics as we know them break down. Surrounding the singularity is the event horizon, often referred to as the point of no return. Once something crosses this boundary, it's gone forever, at least according to classical physics. So, what happens when a star, planet, or even light gets pulled into a black hole? Does all the information about the objects that fall into a black hole get erased from the universe? That's where things get tricky, and that's where the paradox begins. The information paradox explained. In classical physics, there's a rule called the law of conservation of information. This law states that information about any physical system cannot be destroyed. Whether you burn a book, dissolve sugar in water, or smash a vase into pieces, the information about the system's initial state is still present in some form, even if it's spread out or changed. However, black holes seem to violate this law. When something crosses the event horizon, classical physics suggests that all information about that object is lost forever. Once the black hole eventually evaporates due to Hawking radiation, a process we'll explain in a moment, the information appears to vanish from the universe, never to be recovered. But according to quantum mechanics, this shouldn't happen. Information must be preserved at all costs, even in the most extreme environments like black holes. And this is where the paradox lies. How can information be lost in a black hole when the laws of physics demand that it must be preserved? Hawking radiation and black hole evaporation. Now let's introduce another key concept: Hawking radiation. In the 1970s, Stephen Hawking made a groundbreaking discovery. He theorized that black holes are not entirely black after all. Instead, they emit a faint glow, now known as Hawking radiation. This radiation is the result of quantum effects near the event horizon, where pairs of particles spontaneously appear and disappear. Sometimes one particle falls into the black hole while the other escapes, making it seem as though the black hole is losing mass over time. Here's the problem: as the black hole emits Hawking radiation, it gradually shrinks and, eventually, evaporates completely. But when the black hole evaporates, all the information it swallowed should still be somewhere in the universe, right? Quantum mechanics insists that information can't just vanish. So, where does it go? This is the essence of the black hole information paradox. What happens to the information about the things a black hole consumes when the black hole evaporates? Possible resolutions to the paradox. Physicists have proposed several ideas to resolve this paradox, but none are without controversy. Let's explore some of the leading theories. The information is preserved at the event horizon. Some physicists propose that the information isn't actually lost inside the black hole, but rather encoded on the event horizon itself. This is known as the holographic principle. According to this idea, all the information about the three-dimensional objects that fall into the black hole is stored on the two-dimensional surface of the event horizon. Information escapes through Hawking radiation. Another hypothesis suggests that the information is somehow encoded in the Hawking radiation that black holes emit. While this radiation seems random, some believe that, with the right quantum framework, it may carry the lost information in a way we have yet to fully understand. Wormholes and alternate universes. There are also more exotic possibilities, including the idea that black holes might be connected to other universes via wormholes, and that the information could be transferred there. If this is true, the information might not be lost, it could simply be somewhere else in the multiverse. The firewall hypothesis, a more recent and controversial theory, involves what's called a firewall. This theory suggests that instead of a smooth event horizon, there's a wall of high-energy particles that destroy any information entering the black hole. This hypothesis, though highly debated, challenges the traditional understanding of what happens at the event horizon. Information is truly lost. Finally, some physicists, although a minority, suggest that perhaps information can be lost. If true, this would require us to reconsider some of the most fundamental principles of quantum mechanics and physics itself. This would lead to a radical shift in how we understand the universe. Why the information paradox matters. Now you might be wondering, why does this matter? Does it really affect us if information is lost in a black hole? The answer is yes. This paradox touches on the very foundations of physics. It brings into question the relationship between quantum mechanics, which governs the smallest particles in the universe, and general relativity, which explains the behavior of massive objects like stars and black holes. Resolving the black hole information paradox could lead us to a unified theory of quantum gravity, a long-sought goal in physics that would reconcile these two frameworks into a single, coherent picture of reality. Furthermore, understanding black holes and their relationship with information could unlock new insights into the nature of time, space, and the universe itself. It's not just about black holes, it's about understanding the fundamental fabric of reality. The search continues. As of now, the black hole information paradox remains unresolved. Scientists around the world continue to explore new theories and conduct experiments to better understand the nature of black holes, quantum mechanics, and information. One thing is for certain, the answer to this paradox, when it comes, will reshape our understanding of the universe in profound ways. Will we one day unlock the secrets of black holes and discover whether information is truly preserved? Only time will tell. Thank you for joining us today on SCI Discovery Chronicles. If you enjoyed this deep dive into the mysteries of the universe, be sure to like, comment, and subscribe for more explorations of science's greatest puzzles.